Hello. Maybe you are in introductory physics and you want to figure out how to do these relative velocity problems. So let's do it. I'll give you my comments about relative velocity problems at the end. Well, let's just start it. Here's a plane. This is one of the common things, planes, but that's fine. Let's start with hard to medium, easy to medium to hard. That's what we're going to do. Here is the first problem. You've probably seen something like this before. So you can read that. I just put it up there just for reference. Basically, there's a train car with a window on it, and there's a person inside with a baseball or any kind of ball. The train car is moving at 10 meters per second to the right, and the person throws the ball to the right at 5 meters per second. Now imagine there's someone on the ground looking through the window. How fast do they see that ball? It's not a hard problem, right? But we can use this to our advantage. Okay, so here, that light's bothering me. So I can say the 10 meters per second of the car, and then I just add the 5 meters per second from the ball, and I get a total speed of 15 meters per second. See, physics isn't hard. This is a problem because you could see this and say, oh, I don't even really need to think about how to do it. I can just use my intuition and get the right answer, and that's true. But we can also use correct physics to get the answer, and that will help us with problems that you can't use your intuition for. So let's do that problem again. Number one thing that we need to realize is that velocity is relative. If I measure the speed of the train, it's always the speed of the train with respect to what reference frame? Okay, so here I don't have to say it, right? If I say that the car is moving 10 meters per second, well, that's with respect to a stationary ground. I mean, of course, the Earth's moving, the solar system's moving, and all this stuff. So we have to pick a reference frame. And in this case, we're going to use the reference frame of the ground. It wasn't stated, it was implied. When the person inside throws the ball, they also have a reference frame, but it's the velocity of the ball with respect to the car, right? It's not with respect to the ground. And in fact, with respect to the ground is what we want to find. We're trying to find the velocity with respect to the ground. So we can write this as the following vector equation. Notice that those are vectors. We're going to talk about vectors, but I just want you to notice that. The velocity of the ball with respect to the ground is equal to the velocity of the ball with respect to the car plus the velocity of the car with respect to the ground. That's exactly what we did. We just did that. Now here's the little trick. Okay, if you put these subscripts on there, ball with respect to the ground, ball with respect to the car with respect to the ground, then we can match up indices and kind of make them look like they cancel. So here I have car, they match up, right? This one ends in car, that one starts in car. So they kind of cancel, and I get this, ground, ball, right there, ball, ground. So that's one way to think about it. But if we write, you're not going to get any harder velocity addition problems than this, where you can't write it out like that. Okay. Let's use our new tool for a different problem. Again, I have a whole bunch of stuff here. We have water moving at 5 meters per second, and then a boat can travel at, the water is 1 meter per second. I said 1 meter per second. The boat's moving at 5 meters per second, and it's aimed directly across. So that's kind of a hard thing to say, right? But we'll get there. And the river is 500 meters wide. What are these values, right? The water speed, 1 meter per second, that's the speed of the water with respect to the ground. So now I'm just going to say W dash G. So W is water with respect to the ground. And then the 5 meters per second for the boat is actually the velocity of the boat with respect to the water. If I want to match up those indices, I want to find out the speed of the boat with respect to the ground. I can match up the indices to get this equation. Right, there's the boat with respect to water with respect to ground. These kind of are matched up, so I get boat, ground. So that's my vector equation that I want to work with. Now let's use that vector equation. So let's add these as velocities. And I'm going to do this problem twice. So there's my velocity of the boat with respect to water. It's a vector, right? It's pointing up. The velocity of the water with respect to the ground is a vector that way. And how do we add vectors? Well, if you add them graphically, if you put the beginning of the next vector to the end of the first vector, then the resultant vector is from the beginning of the first vector to the end of the last vector, and that's my velocity of the boat with respect to the ground. This is graphically the same as that. It's the same equation, it's just done graphically. And then there's some angle theta right there. what we have here is something that's kind of easy because we've formed a right triangle. Because the velocity of the water with respect to the velocity of the boat with respect to water are perpendicular, I make a right triangle, and now I can use just right triangle stuff, right? If I want to find the magnitude of this, I can use the Pythagorean theorem. So the this velocity, the magnitude, is going to be the square root of this squared plus that squared. And then I can find the angle, again, using right triangle. I can use the tangent. Tangent is opposite over adjacent, so my tangent is that right there. Okay, let's go ahead and calculate this stuff. So here's my velocity of my boat and the velocity of my water. I can calculate that just by putting my numbers. 5 squared plus 1 squared. I dropped off the units because it was going to be too tedious. 5.1 meter per second. And that looks like that. Then I can find the angle, put in the velocity of this opposite over adjacent, and I get 1 over 5, take the inverse tangent using right degrees, and I get 11.3. And then one of the questions was, how long does it take to cross and how far down does it go? That's a common question to ask. So there's my angle. That's the path that it's going to take, and that angle is the same as that angle. I know this length is 500 meters. I need to find this length right here. Well, the cosine is going to be equal to adjacent 500 over hypotenuse, which is s. And I don't know s, but I know theta, and I know the 500, so I can solve for s. It's just going to be 500 divided by the cosine 11, 510. Now I can find I can write the velocity as the change in position over change in time, delta s over delta t, and I want to go this whole distance of s, and I want to solve for delta t. So just solving this equation for delta t, I get that, and then putting in my values, I get 100 seconds. Yay, awesome. Now, how far down did it go? I already know this distance s. If I want to find x, there's multiple ways I could do that. I could use the Pythagorean theorem, though, and say x squared plus 500 squared is s squared, and then solve for s, and I get 100 meters. Now, there is another way to do this problem. I just want to point out, I solved this the way that makes the most sense. In the reference frame of the river, if you just want to find out how long it takes to go across, you can just say, well, what's its velocity is straight across, right? And I don't really care that it's moving horizontally. And you can use that 500 and that 5 meters per second to get the same time it takes to get across. And then you can use that time to find out how far the river moved, and you get the same answer. But I just really want to talk about relative velocity. So now, there's another way to deal with this, and that's to deal with these as vectors. And so if just a vector view, I'm not doing all the vector stuff, but imagine I have some vector v with some angle with respect to the x-axis like that. I can write this vector as a sum of two other vectors. One is this vector vx times x hat. And here we're using x hat. Your book may use I hat, j hat. It may do other form, but it's all the same. And x hat is just a way to say the x direction. It's a unit, what we call a unit vector or a direction vector. It tells us the direction of x. And that makes it this as a vector because vx is a scalar. Plus a vector in the y direction, vy, y hat. So you can see here, if I graphically add, that's the y hat thing. If I graphically add vx, x hat plus vy, y hat, I do indeed get that vector right there. So that's kind of a good thing. Where was I at next? Let's see. Oh, there we are. Okay. So that's how I'd write it in an equation, right? That's the same thing. Here's my x direction and there's my y direction, and that's how we can express this vector in terms of how much it is in the x direction and how much it is in the y direction. How do we find vx? Well, if I know the angle theta and I know the magnitude of this is just v, then I can say the cosine of theta is vx over v, and I solve for vx, I get that. And I can do the same thing using the sine for vy, and I get that. Now be careful, because this only works if my angle is measured from the x-axis, which it is always not. You always want to draw this triangle and say, okay, adjacent over hypotenuse, opposite over hypotenuse, and for sine and cosine, but that's that. Now, what if I have two vectors? Why do I care about breaking this into what we call component form? Suppose I have two velocities, which is what we're doing, v1 plus v2 equals v3. Well, it turns out that I can write the vector v3 as the sum of the x components and the sum of the y components. So if I know v1 and v2 in terms of x's and y's, I add the x's together and I add the y's together, and that is my resultant. It's kind of cool. And then I could find the magnitude by taking the magnitude using Pythagorean theorem for the x and the y components right there. So it's really a great thing, trust me. Let's go back to the river problem. Here's the river problem, the boat going across the river, and there is our vector equation that we had the same thing before. Okay, but now I want to write these all as vectors in component form. So the velocity of the boat with respect to the water is going this way. It's going straight up, and we'll call that the y direction. So it's pretty easy to find components. It's not moving at all in the x direction, and it's moving 5 meters per second in the y direction. So there's my vector for that right there. I can do the same thing for the water with respect to the ground. It's just moving in the x direction. So it has 1 in the x direction and 0 in the y direction. That's not hard. Now I can add those two together, right? That's what this equation says. Add these two vectors. Well, I'm going to add the x's, I'm going to add the y's, and I get 0 plus 1 plus x hat plus 5 plus 0 y hat, or 1 x hat 5 y hat. Yay! Now I can find the magnitude of that by taking just, you find the magnitude of any vector, 1 squared x squared plus y squared square rooted 5.1. Done. Okay, we're going to do another problem, but I have to take a little side detour, and we need to talk about directions and wind, and in respect to like flying and stuff like that. That's the actual compass right there. See, it's got headings on there. We're going to talk about that. But here's your northwest, east, south stuff. Imagine that I have a wind blowing in that direction, and I measure it like this. I measure the angle between that vector and the east direction is 10. Well, how would I describe that? Well, I would just draw it. But a lot of times in the book, they would say that's 10 degrees north of east, because you're starting at the east and moving in the north direction, 10-degree rotation. And north, if you just say it's a north wind, or the wind is north of east or whatever, when they say wind, it means that's the direction that it's from. And I always get that confused. It's hopefully not going to stop you from solving the problem, because it's just a way we talk about those things. Okay, here's another example. Imagine we have a velocity in that direction, and this angle is 20 degrees. That would be 20 degrees west of north. Oh, that's not. It says west of east. That should be west of north. Sorry. Okay, let's just skip that page. It's dumb anyway. The other way is to measure the angle with respect to the north. And this is what we call heading or bearing. I just picked a direction, and this is the compass on my iPhone. So if you're headed straight north at 0 degrees, straight east is 90 degrees, and so this is heading at 38 degrees northeast. You don't even have to put the northeast, you can just say 38. Let's do some problems now. One more problem, and this one is challenging. This one's a tough problem that if you try to intuition it, you're going to not have a good time. This is a plane landing in a crosswind. It's pretty cool. So you can see the direction of the runway, and the plane's moving in the direction of the runway, but not aimed in the direction of the runway. And so let's set up a problem like that. And then you have to do this really difficult thing of once the wheels turn down, you got to rotate back in the direction of I'm not a pilot, so I just imagine that's hard. I couldn't even do this in a video game probably. Here is the problem. A plane has a airspeed of 80 meters per second, and it wants to land on a runway that's directly east with a 20 meter per second wind. And here I did the thing just to make it kind of realistically stupid. 20 degrees is 20 meters per second, 25 degrees east of north. So here's your wind. So that's west of north. I'm just messing up double bad. I'm gonna fix that in the I want to fix it right now. I'm not going to fix it right now. That's the direction. Okay. I did the problem with that direction. Mistake. I'm not redoing the video. And then so the question is, which way do you have to aim the plane to land? Right? And so you'll see here that if you try to just draw the right triangle, it's not going to work. Things are not right triangles. But I can label my velocities. This is the velocity of the plane with respect to the air. And this is the velocity of the air with respect to the ground. It's the wind, yes, but that's the way we write that. So let's just draw our vectors in this coordinate system here. So there's my wind, and that's west of north, west, 25 degrees. And that's the direction that I want to land in. And that's what I'm going to call, it has a magnitude of VL. I don't know how fast it's going. I don't know that value. I do know I want it to end up in the east direction. And then this is the velocity of the plane with respect to the air. I know the speed, but I don't know the angle, right? I don't know I want to find that angle. But still, I can write my equation, velocity of the plane with respect to the ground, plane, air, air, ground, it works. Now, in this case, I want to solve for that. I want to solve for VPA. So what I can do is subtract this vector from both sides. You can treat vectors like that. It works. Addition and subtraction works. And I get, by subtracting AG from both sides, I get PG minus AG. And they don't match up here, right? And that's fine, because it's not the right equation. This is the equation that you want to start with. Okay. Now we just need to write these in component form. So the velocity of the air with respect to the ground is this way, right? So I'm going to call this the y direction and the x direction. Notice here that the x direction is right here. So that's the opposite side of that angle. So I'm going to use sine for x. And I know it's in the negative x direction. So I'm going to put negative, the speed, 20, sine of 25. For the y direction, the north direction, I'm going to use the cosine because that's the adjacent side of that right triangle. So this is one of those examples where you can't just say sine is y and cosine is x. It doesn't always work. Be careful. So I get 20 cosine that, but it's in the positive y direction. Now what about the velocity of the air with respect to the ground? The airplane. No, that's air with respect to the ground. Oh, no, I'm sorry. I was looking at my things. So I'll do is, this is just calculating this. So 20 sine 25 is 8.45, then the negative sign, and this is 18.12. For the velocity of the plane with respect to the ground, I don't know the value, but I do know that it has no y direction. It's only in the x direction. So I'm going to call this value VL, the landing velocity, just for fun. But that's the magnitude of the speed, and the direction I know is in the x direction. Now I can write a vector for this too, right? I can write this as a vector. I don't know the angle, but I can still write it. So here I have the adjacent side of that triangle is going to be cosine theta. So its speed is 80. So it's 80 cosine theta. So that's my x component. The y direction right here is in the negative y direction. It's the opposite. So I get 80 sine, negative 80 sine theta. So I know all my vectors up here. I know these two vectors. So I can just calculate what I need to know. So there's my equation. That's the same equation. I just wrote it down. Here, this right there is PA. That's the velocity of the plane with respect to the air, right? Boom, boom. I should have calculated. Oh, didn't calculate. I didn't know theta. This is the velocity of the plane with respect to the ground. And I left the 0 there just to make it look fun. And then finally, I have this term right there, negative. And there is a negative, right? A negative vector. I have to multiply each component by negative. Now, since I have a vector equal to a sum of vectors, one way to do this is to say the x component of this vector has to be the x component of this vector. So the x component here is 80 cosine theta. The x component over here is going to be VL plus 8.5, right? Because I have x hat. So, and there's negative of negative is positive. So that is an equation. Now, I can't solve it because I don't know theta and I don't know VL, but there it is. If I do the same thing for the y, here's my y velocity, negative 80 sine theta, and that has to be equal to this y velocity, which is 0 plus negative 18.12. So there's my second equation. Now that one I can solve, right? The only thing I don't know in there is theta. So if I divide both sides by negative 80, I get sine theta is 18.12 divided by 80, the negative signs canceled. If I take the inverse sine of both sides, I get theta, and I get a 13.9. That's the answer, so I'm going to put a box around that. Now I can use this angle and go back up here, and I actually can solve for the landing velocity. So if I put in theta is 13.9, I get cosine theta 13. Oh, that should be, I made another mistake. Okay, I forgot to subtract off that to get the VL. But there you go. That's the landing velocity. And I cut it off with my face anyway, so who cares? But you get the idea. Box, even though it's wrong. Okay, so here we have our plane landing in the wind, which I got the direction wrong. But the most important thing, I want to describe this in terms of like how you would see it. So this is my velocity vector, and there's my angle, 13.9. And the question is, which way should you aim? And so one way you could do this is say 13.9 degrees south of east, because here's east, that way is turning towards the south. The other way is to say, okay, well, there's 0 degrees straight north, 90 degrees straight east, and so this is going to be 13.9 plus 90, which is 103.9 degrees, and then that would be your heading on the compass right there. And there you go. Now, I told you I would tell you my feelings about these kind of problems, and in the introductory level courses, I hate them, right? Because they don't really build. Nothing else builds on it. I mean, yes, relative velocity is important, but nothing builds on it. I skip it usually, unless they need it for something else, because I'd rather focus on how do we describe velocity and position and time and acceleration. What do we do with acceleration? What about momentum? What about work energy? There's so many other things to do, and this is kind of like a side quest. A side quest in the game of physics, and I just don't think it's worth the side quest and the extra experience points, and there's not that much loot. So if you're teaching this and you have the option, I would skip it unless you have time. And also, I think students find it very confusing with the east of north, north of west, and all that stuff. So there you go. I mean, I actually, I'll take it back. I do talk about relative velocity, but I only do very, 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 very simple ones, and then I move on just so I can say I did the box. Okay, there you go. Relative velocity problems. I'm not going to do it again. I probably will, but hopefully not for a while, because I don't like these. The end. Talk to you later. I already gave you a thumbs up. There's another one.